Before we start talking about motion in two different dimensions, say a horizontal and a vertical, we need to talk about how vectors work in both horizontal and vertical directions at the same time. So we'll start off with a quick example here, just a very easy example. Let's say that we walk this direction 6 blocks in the city, and then we walk 3 blocks that direction. Two things I want you to notice about these vectors. First, we start, with the direction we're heading, and we have an arrow at the end. That's how we draw vectors, with arrows. You'll notice that these two are perpendicular to each other. So if we wanted to, we could actually draw a right angle there. And then notice I've tried, at least, to draw them sort of proportional to each other, in that my 6 blocks vector is longer than my 3 blocks vector. It turns out that by drawing things, say, to scale, even if we were to draw maybe, if 1 block were a centimeter and we did 6 centimeters and 3 centimeters, we could actually find the result of these two vectors and where we ended up by measuring and using a protractor to get angles, things like that. So we can actually draw these to scales, and that's the method that we're going to talk about first. So the first thing we're going to do is add vectors together graphically. Okay, so imagine just doing these all on a graph, on an XY plane, and we're going to, although I can't really do it on here, we're going to pretend that these are all drawn to scale, and if you actually drew them to scale, it would work out perfectly. So when we add two vectors together, what we do is we start with a method called head to tail. And I've actually already drawn these vectors head to tail. So the way it works is you draw your first vector, and then at the head of that vector, you attach the tail of your next vector and add them together. And you could do this for as many vectors if you wanted. If we wanted to draw 3 vectors, you'd just attach the other one right to the head of that one, the tail of that third vector to the head of my second vector, and we could continue on. The result of adding these vectors together, which is called the resultant, is just from where we started to where we ended. Kind of like displacement, where it's just the difference between where we start and where we end. And that's called our resultant. So our resultant is what we get from adding the two vectors together. So graphically, this is how we'd add them together. And we should know from trig how you could find this resultant would be Pythagorean Theorem. All right, a squared, or resultant squared, in this case, would be b squared plus c squared, so the two sides. So our resultant squared, in this case, let's go ahead and solve for it, would be 6 squared plus 3 squared. And so our resultant would equal, in this case, 6.71 blocks. Now notice a little detail here. Notice every vector on my triangle has the exact same unit, in this case blocks. That's very important. We can't mix, say, meters and meters per second into the same vector and add them together. It doesn't work like that. You have to have all meters per second, whatever it is, it all has to be the same unit. Now with vectors, we also have to include a direction. We're usually going to include that direction by looking for an angle. That angle in this case we could find using the tangent function with trig, so tangent of theta would equal my opposite side over my adjacent side, so in this case 3 over 6. So we'd solve for theta, so theta would equal the inverse tangent of my 3 over 6, which would be 26.57 degrees. So that would be our full result, would be 6.71 blocks, 26.57 degrees, in this case maybe north of east, right? If this direction were east and that was north. So now we want to look at a case where maybe we would subtract vectors. So if we're going to subtract vectors, so in the last case we had 6 blocks east and 3 blocks north, and we added those together using our head to tail, so maybe now we'll subtract them. Okay, and I'll call them meters this case, so maybe 6 meters, and we went east minus 3 meters north. Okay. Well, if we're going to subtract vectors, right, we'll draw them out since we're doing our graphical method here, 6 meters, but then instead of drawing 3 meters north, I just draw 3 meters in the opposite direction. So anytime we're subtracting, you just flip that last vector. So in this case, my 3 meter vector, we're just going to flip that around, and that subtracts it. And then we have there our resultant vector. And if we went through the math, right, since it's the same vectors, just opposite in direction, we'd still get the same answers that we had before, right? We'd get same resultant, because it's just Pythagorean Theorem, and we get our same angle, our 26.57 degrees, but this time that angle would be south of east instead of north of east. So we've done a little bit of addition, a little bit of subtraction. We can also do multiplication. And when we multiply vectors, all we're going to do is multiply them by a scalar, right? So I might take my, 6 meters east and then multiply it by the scalar 3. So if I did that, 3 times 6 is 18. So my original vector would have been this, 6 meters to the east. And by multiplying it, all I'm doing is changing the length of the vector. So if I multiply it by 3, 3 times as long, and so now it's 18 meters to the east. So all the scalar is going to do is just change it. If I changed it instead of 3, right, I multiplied it by a half, then it'd be half as long, and it'd be a 3 meter long vector. Right, so multiplying by a scalar, which is all we're going to do, is just going to change the length of our vector. Another very important skill to have is called resolving vectors. This is something we're going to do a lot in this chapter, so it's something that you need to get good at. For example, let's say I throw an object with a velocity of 30 meters per second, but I throw it at an angle of, let's say, 15 degrees to the ground. Okay, and what we'll need to figure out, because vectors act, remember, independently in our x and y directions, which is something we mentioned very briefly, and it's something that's going to be very important here in a little bit. We might want to be able to find, say, our x component of that vector, is the word we use, and our y component. So that would be our y direction, our vertical direction, and x, our horizontal direction. I might need to know what's my velocity in the horizontal direction, what's my velocity in the vertical direction. That's actually going to be a big part of the problems that we work here in a little bit. So if we go to find our x direction, right, that's the, if we think about trig here, we have our hypotenuse and we have our adjacent side to the angle. So adjacent and hypotenuse, if we remember SOHCAHTOA, it was my cosine part. So if I want to find x, I'm going to use cosine. So we'd say cosine of 15 degrees for x is equal to my adjacent side, x, over my hypotenuse, 30 meters per second. Okay. So in order to find x, I multiply both sides by 30 meters per second. So x is going to equal my 30 meters per second times the cosine of 15 degrees, which is equal to 28.98 meters per second. So that would be my velocity of this object that is just in that x direction, just in my horizontal direction. So then to go find the y direction, well, that's the opposite side on my triangle. So I have a hypotenuse and opposite, so that's my sine component. So sine of 15 degrees is equal to y over 30 meters per second. So y is equal to 30 meters per second times the sine of 15 degrees. So y is equal to 7.76 meters per second. Okay. Now that might seem a little unreasonable in the way that I've drawn my triangle, but I didn't really draw my triangle to scale here. This 15 degrees probably should be a little shallower, maybe something like that. But the process remains the same. Now you can take a couple shortcuts here, right? If we know our initial velocity at our angle, the y component will always be that times the sine, and the x component will always be that times the cosine. Now that may not be true in later chapters, but it proves to be a good shortcut now if you can remember that. So if a problem asks you for the velocity in the x direction, you can immediately jump to cosine times your velocity. If it's asking you for the velocity in the y direction, you can immediately jump to sine times that velocity. So a nice little shortcut there.